The use of automatic spray equipment to apply dye release agents is an important aspect of the die casting process. However, the equipment utilized in the application of these products is often implemented incorrectly. The purpose of this video is to explain the equipment, the utility requirements, and the effect certain adjustments have on spray atomization. The quality of the atomization will also be studied in an experiment that shows how large droplets and small droplets affect heat removal. The amount of fluid used and the amount of fluid wasted for both conditions will be observed during an experiment. Finally, troubleshooting of common problems will be shown. To understand how to properly use the spray equipment, it is important that the terminology of the equipment be fully understood. Starting from the valve package and ending with the nozzle tip, each item in the system will be explained. The valve package is responsible for controlling the air and liquid supplied to the nozzles. The most common valve packages used control the flow of fluids and air to one or two manifolds. However, complex valve packages comply up to 3 different fluids. Some of these manifolds can even dispense 2 different fluids through the same nozzle tip. There are 3 valves responsible for the spraying operation on single lube valve packages, and 6 valves for 2 lube units: the spray air valve, the pilot valve, and the lube safety valve. There is also a blow-off valve that controls the blow air used to spread out any residual dye lube. The spray air valve is an electrically actuated valve that controls the spray air or atomizing air. The regulator in this circuit is responsible for adjusting the atomization. When the pressure is increased, the droplets of lube become smaller. When the pressure is decreased, the droplets become larger. When operated with Rimrock controls, a program parameter can be set to allow the spray air valve to stay on longer than the pilot valve at the end of the spray sequence. This programmable feature is called the Purge timer. The pilot valve is an electrically actuated valve responsible for 2 functions. The output of the valve is connected to a T-fitting. One end of the T-fitting is used to pneumatically actuate the lube safety valve. The other end is used to lift the pistons in each nozzle. When lifted, these pistons allow the lube to flow through the nozzles. There is a regulator associated with this circuit. It is used to adjust the pressure of the pilot line. If the pilot pressure is insufficient, the pistons will not lift and the lube will not flow. The recommended pressure for this regulator is between 60 and 80 psi. This pressure setting has no effect on the quality of the atomization. It is only used to lift the pistons in each nozzle. The pilot valve is a 3-way valve. When actuated, air flows to the pistons. When the valve is not actuated, it is exhausting this air to atmosphere. If this air is not allowed to exhaust, the pistons will remain lifted and the nozzles will continue to leak fluid. Because a 2-way valve does not exhaust the atmosphere, it is imperative that this valve only be replaced with a 3-way valve. It is also important to keep the exhaust muffler on this 3-way valve clean. If it becomes clogged, it will behave as if it were a 2-way valve. The lube safety valve is a pneumatically actuated 2-way valve controlled by the output of the pilot valve. The purpose of the lube safety valve is to allow fluid to flow through the lines only when fluid is called for. The design of the nozzles will allow pressurized lube to remain at the nozzles all the time. In this case, the pilot piston would be responsible for turning on and off the flow of lube. However, because a leak can occur on the moving hoses, an undetected leak on an idle machine could cause a large amount of dye lube to be lost. The lube pressure supplied to the valve package should not fluctuate. If the pressure is allowed to fluctuate, problems with the quality of the spray can be expected. If the lube pressure drops, this can cause the nozzles to stop spraying lube. Only spray air will be expelled from the nozzles when this happens. If the lube pressure becomes too high, this can cause the size of the droplets to become very large and cause the lube to back up into the spray air lines of the valve package. If the lube pressure being delivered to the valve package fluctuates, it is recommended that the user install a regulator to keep the lube pressure constant. For example, if the incoming lube pressure fluctuates between 60 and 80 psi, a lube regulator could be installed and set to 50 psi so that the fluctuation will not be seen by the valve package. This will help keep the atomization constant. The hoses from the valve package terminate at the manifold bar. The nozzles are mounted to the manifold bar. Manifold bars can be single or dual lube. When the blow valve is actuated, air will flow through these copper tubes mounted on the blow-off manifold. These tubes are used to spread out any residual dye lube. It is important to keep all of these tubes in place and to keep the ends pinched down. If not, a large amount of air will be lost and the air blow-off will not be as effective. Dual lube manifolds are used for several different purposes. Sometimes the same fluid is put through both manifold bars, then the nozzles are set at different intensities, such as when more lube is required on the ejector die and less lube on the cover die. Different fluids can also be used through each manifold. Water could be used through one manifold bar to initially cool the die. After the initial cooling has taken place, dye lube can be run through the other manifold to lubricate the die. In some cases, two totally different types of lube can be used for different areas of the die. The use of a two-lube manifold is only limited by the imagination and needs of the end user. There are two styles of manifolds that can be purchased: standard configuration manifolds and custom configuration manifolds. Standard configurations consist of a row of nozzles lined up against each other. This configuration typically requires the reciprocating device to use a sweeping motion to cover the die. A standard manifold offers the advantage of being able to accommodate several dies with only a few small adjustments to the individual nozzle tips and the reciprocator's program. The standard manifold is often used for short-running jobs where it is difficult to justify the purchase of a custom manifold. The disadvantages of a standard manifold are longer spray cycle times. The standard manifold will also require more dye lube than a custom manifold because all parts of the die are sprayed. Custom manifolds are built for a particular die or a family of similar dies. The custom manifold typically needs only one spray position. All the necessary areas that need to be sprayed are done so at one time. Custom manifolds can give the user a 15 to 25% reduction in spray cycle time. Some users buy one custom manifold per die and include the manifold cost in with the tooling cost. The manifold is stored with the die and is considered part of the tooling. The 025 nozzle is made up of several basic main parts: the body, piston, metering device, extension tube, nozzle head, nozzle seat, and nozzle tip. The body is made from a machined block of aluminum that has been anodized to prevent corrosion. It is the main element that contains the following components and allows other components to be connected to it. The piston is operated by pilot air. The pilot air lifts the piston against the spring. Once the piston has been lifted, lube is allowed to flow into the nozzle. The lube will flow through a metering device, which is normally a metering screw. Metering devices come in three configurations: a 40-degree pitch metering screw, a 2.5-degree pitch metering screw, and a fixed orifice. The 40-degree pitch metering screw is a standard metering screw. The 2.5-degree pitch metering screw is considered a fine metering screw. The difference between the two is the resolution between clicks. The 2.5-degree pitch screw allows for higher resolution between clicks. In either case, the metering device is what is used to control the amount of fluid that flows through the nozzle. Since the size of the spray tip can affect the pressure required for atomization, the metering screw is oftentimes the only way proper atomization can be achieved for a particular nozzle. Another alternative to the metering screw is the fixed orifice. It takes place of the metering screw. The metering screw is unscrewed from the body of the nozzle and replaced with the fixed orifice. It has a hole drilled in it that is equivalent to the same area as the number of clicks on a standard metering screw. For example, if an area of 65 thousandths exists when the metering screw is clicked out 5 clicks from being fully closed, a fixed orifice could have a hole drilled equal to that area. Because of its shape, the fixed orifice is less likely to clog than the metering screw. Another advantage to the fixed orifice is that it is non-adjustable, thus preventing unauthorized adjustments. Attached to an aluminum pipe nipple to the body of the nozzle is the spray head. Spray heads come in different configurations. A single head is like a pipe elbow that simply diverts the flow from an aluminum pipe nipple to a 90-degree angle outward towards the die. Double heads resemble a pipe T and function in the same manner. It equally splits the flow of fluid in opposite directions. Diverter heads are a very popular head that resemble a pipe T, but with an adjustment that allows the user to vary the flow of fluid from the ejector die to the cover die. In some ways, it allows the user to accomplish the same task of a 2-lube manifold with a single lube manifold. The coin slot in the adjustment portion of the head contains a device similar to a ball valve. Nozzle seats are used to help to keep the nozzle tip from moving around as the unit is running. The seat can be green polyurethane or brass and is placed directly behind the nozzle tip. When the green seat is used, some adjustability is allowed. When the brass seat is used, once the lock ring is tightened, it is nearly impossible to readjust the nozzle without loosening the lock ring first. The lock ring helps keep the nozzle in place and allows for adjustment. Nozzle tips on the O25 come in 11 standard types. Nozzle tips can be classified into 2 categories, cones and fans. The cone sprays a conical pattern. The fan sprays a wide horizontal pattern. There are several different varieties of each nozzle tip. The ability to supply the correct volume of liquid as well as air is extremely important for proper atomization to take place. By looking at the flow requirement chart, we can see with a lube pressure of 50 psi, one O25 nozzle can deliver up to 2 gallons a minute. The viscosity of the liquid, restrictions in the line, metering screw settings, nozzle tip size, and pressure variances will have an effect on this parameter. Since most manifolds have more than one nozzle, using this chart as a guide can be helpful when doing calculations for lube requirements. Adequate airflow is also a concern. With the spray air pressure of 60 psi under dynamic conditions, 10 cubic feet per minute is required for each nozzle. 10 nozzles on a manifold will put airflow requirements at over 100 cubic feet per minute. Any restrictions in the lines will prevent the needed volume of air from reaching the nozzle. When using the chart to calculate the flow requirements, it should be understood that the pressures listed are dynamic pressures. 2 types of measurable pressure readings are static pressure and dynamic pressure. Static pressure is the pressure in a line or a vessel when fluid is not flowing through it. If one were to take a pressure tank, fill it to 80 psi, and then shut off the valve that was delivering the air, you would have 80 psi of static pressure. If a valve is open and the pressure running through the pipe is red, it would be pressure under dynamic or running conditions. Since the size of the pipe that the air is flowing through will affect the dynamic pressure, only the dynamic pressure should be used when doing calculations or adjustments. The quality of atomization is affected by several parameters. The parameters that will be discussed in this video are the lube pressure, the spray air pressure, the nozzle tip size, and the metering screw adjustment. Remember, before making any adjustments to the equipment, make sure all applicable safety protocols, such as lockout-tagout procedures, are followed. Also, the material safety data sheets for the fluids worked with should be consulted so any needed safety equipment can be worn prior to working with the fluids. The best way to start the setup of a manifold is to begin with the dynamic lube and spray air pressures set equally. 50 psi is usually a good pressure to use because most systems can deliver these pressures. This setting should allow any manifold to spray. The next thing that should be attempted is to increase the spray air pressure. How much higher the spray air pressure can go above the lube pressure depends on the size of the nozzle tips, the number of nozzles, and the distance between the furthest nozzle tip and the input of the manifold. The size of the nozzle tip has a great impact on how much differential there can be between the lube pressure and the spray air pressure. If the nozzle tip is large, such as in the number 4 nozzle tip, one can expect to see dynamic pressures at 10 to 20 psi above the lube pressure, and the nozzle will still operate. Anything over 20 psi will usually cause the nozzle to cut off. If the pressure differential between the lube and spray air is brought closer together or even equalized in the case of the number 4 nozzle tip, the size of the droplets will be extremely heavy. In the case of the smaller nozzle tips, such as in a number 1 or a number 5 tip, the pressures need to be closer together. If the spray air pressure is brought much above the lube pressure, the air will overtake the lube and the nozzle will cease to spray. It is important to realize this when multiple tips are used on a manifold. It is also important to realize in longer manifold bars, as the spray air pressure is gradually increased, the nozzles which have the most restriction, or the nozzles on the end of a manifold bar, will tend to cut out first. As the pressure is increased, more and more of the nozzles will cut off until none are spraying. In order to compensate for this effect, the metering screws can be used to balance the amount of atomization through each nozzle. You're going to adjust the number 4 tip. It's spraying rather heavy. The purge adjustment is an adjustable timer that helps purge excessive lube from the nozzle. When the spray operates, the pilot valve, lube safety valve, and spray air valve open together. Electrically, there are 2 outputs which operate the pilot valve and the spray air valve. However, when it is time to shut off the spray, the pilot valve shuts off first. This will close the pilot valve and the lube safety valve, thus shutting off the liquid flow. The spray air valve will stay on until the purge timer expires. This will purge any excessive lube from the nozzle tips to prevent dripping. Here's a closer look at how 2 different pressure settings can make the nozzle behave. For this demonstration, the spray will be shot using a normal video camera, then in ultra slow motion, and finally with an infrared camera. Data for each setup will be displayed following each demonstration. For the first demonstration, an 025 nozzle has been set up to spray with 50 psi of spray air pressure and 40 psi of lube pressure. The video shows most of the spray is turning into steam. This is verified by watching the high-speed video. The droplets coming out of the nozzle are small as they hit the plate of steel. The droplets completely turn into steam and little or no fluid is left to drip off the face of steel. The infrared image shows that the temperature of the steel does not change rapidly, but when the target temperature of 275 degrees is finally reached, the steel remains at that temperature. The data on this run shows us that the time to reach the target temperature was 127 seconds. The amount of lube used to reach the target temperature was 16 ounces, and only 1.7 ounces of runoff were collected. In the second demonstration, an 025 nozzle has been set up to spray with 40 psi of spray air pressure and 50 psi of lube pressure. The video shows that most of the water is running off the steel. The high-speed video shows that the droplets are heavier. When the droplets hit the plate of steel, they immediately bounce off and become airborne. In a matter of seconds, the entire area in front of the plate of steel is covered with runoff. The thermal image shows that the plate is cooled rapidly, but once the spray is stopped, the heat immediately starts to build back up. The data on this run shows us that the time to reach the target temperature was 36.5 seconds. The amount of lube used to reach the target temperature was 40 ounces, and 29.5 ounces of runoff were collected from the drip pan placed under the steel. One of the complaints a maintenance technician may get is that the nozzles will not spray. A technician should check for electrical problems. Look at the LEDs next to the output modules on the I/O rack for the pilot and spray air outputs. check to see if they are lighting. If so, check to see if there's a voltage output. If there is no voltage output, shut off the AC power. The output module may be bad, the pico fuse may be blowing, or there may be a loose connection in the wiring. The voltages can be checked at various points up to the valve package. Plumbing problems could also cause a nozzle not to spray. An occurrence that can be confusing to a technician is a unit that will spray in automatic mode but not in manual mode. This is usually due to a crossed hose or wire between the Lube A side and Lube B side. One obscure problem that can be very difficult to troubleshoot and find is a hole in the pilot line. A nozzle can even be removed, and when the pilot is actuated, air can be felt coming out of the pilot hole, but for some reason the nozzle will not spray. If there is a hole in the pilot line, the pressure will not build and the piston will not lift. In that case, one can do a pressure hold test. After shutting off the incoming air and lube pressure, manually activate the pilot valve. When doing this, you should not see a rapid drop in pressure. The pressure should hold until the air normally escapes from the weep holes in the valve. If the pressure falls rapidly, a leak in the pilot system exists and should be repaired. Another occurrence that can cause nozzles not to spray are incorrect pressures. If the spray air pressure is allowed to get too high, or if the lube pressure is allowed to get too low, the air will cut off the lube pressure and the nozzle will not spray. Sometimes nozzles will leak. When a nozzle leaks, one must ask the question, is it one or two of the nozzles, or is it all of the nozzles? If all of the nozzles are leaking, one thing to look for is a plugged pilot muffler. To demonstrate this, we have replaced a pilot muffler with a plug. Because the pilot system operates on a three-way valve, when air is introduced, the pistons are lifted. Once the air is removed, this air must be exhausted to atmosphere. If the air is not allowed to escape, the pistons will remain pulled, and when the pilot system is shut off electrically, the pistons will still be raised with lube flowing out of the nozzle tips. Something that can be likened to the plugged pilot muffler is the replacement of this three-way valve with a two-way valve. Users that have done this have found that the two-way valve will not allow the pistons to fall rapidly, and leakage will occur after the nozzles have shut off. Sometimes backwards wires and hoses can also cause this problem. The purge timer will shut the pilot valve off first and allow the spray air to continue. If these two wires are crossed, the spray air will be shut off first and the pilot will remain on. This will cause the liquid to continue to flow. The last thing to check for is broken springs. Typically when springs are broken, only one or two of the nozzles will leak. In the case of a system that has been severely neglected, all of the springs may be broken. Sometimes one may inherit an incorrectly installed system. Even so, many steps can be taken to improve these systems. In most cases, the root cause of problems in the installation is insufficient line size or restrictions in the lines feeding the lube or air supply. The following example shows the difference between a system supplied with properly sized airlines versus an improperly sized airline. Here is an example of a correctly installed system. Notice that the difference between the static pressure and the dynamic air pressure is not very great. Here is an example of an incorrectly installed system. Notice that the difference between the static air pressure and the dynamic air pressure is extreme. If the size of the feed line cannot be increased easily, some users have been known to implement the following improvements. If the lube supply is in question, after removing as many restrictions in the line as possible, the delivery pressure can be increased and lube regulators installed at each valve package. Bladder accumulators can also be installed to help correct inadequate lube supplies. If the lube supply is split to supply two sides of the plant, the ends of each line can be connected together. This will help to equalize the pressure throughout the line. The extra pipe will also act as an accumulator. The same steps can be taken for airlines, except bladder accumulators would be replaced with a pressure vessel. Aside from periodically rebuilding the nozzles, cleaning the lube filters, checking for broken springs or worn O-rings, spray maintenance should be minimal. One preventative maintenance suggestion is to flush the spray lines. Occasionally, nozzles can become clogged. Usually this is caused by bacteria buildup in the dilube itself. Perhaps the first thing one should do is to contact the lube supplier to see what they can do to help. As far as the rimrock equipment is concerned, flushing the nozzles out periodically during dye changes or on some other scheduled basis is recommended. If a bypass valve is installed prior to the valve package, a hot water and soap solution, or whatever the dilube manufacturer recommends, can be flushed through the nozzles when required. This video has shown the location, function, and name of each spray component, the importance of supplying the correct volume of liquid and air, the adjustments, and what effect the atomization can have on the spraying process, and finally, troubleshooting and maintenance of the spray system. I hope you have found this video informative. As always, if there are any questions, please call me at Rimrock. Thank you.